Hello, Maurieo. In this video we're going to look at applying sea level correction. So here's our diagram. We've got here our typical station A and up here B, and the RL at A is HA, the RL at B is HB. We measure a line between them, which we then reduce to the horizontal, and when we reduce it to the horizontal we say that it's correct at the mean height, which is HA plus HB over 2. So the RL of A plus the RL of B divided by 2. This gives us the mean height. Now, in cases where this is quite high, this can be considerably different to what the same height would be at sea level. And here I've got A, B at sea level. Now, for cadastral purposes, we like to reduce our distances to sea level, or increasingly, as we're talking about now, the geoid, or we use geoid heights, which is the geoid pretty much approximates sea level, and for the most cases it does, but in some cases if it's more than like 6 meters, then we've got to have a serious look. And the geoid is the reference plane for ellipsoidal heights, and the geoid is defined by the ellipsoid, whereas our other heights, which we tend to call orthometric heights, they are their level surface or defining plane, sort of in generic terms, is sea level. We talk about heights above sea level. So here we are. If we take our verticals as we do into the center of the Earth, we have the radius of the Earth 6374000 meters. That's an approximation, 6,374 kilometers. Now, so let's have a look. HA is the RL at A, HB the RL at B. We've talked about the average height. D is the horizontal distance measured in meters. So this is the D here is the actual horizontal distance that we measure. Now the sea level correction as such, and here's our Earth's radius. The sea level correction as such is HD over 6374000. And just to make that nice and easy to deal with, that's equal to HD, where they're all in meters, times 15.69 times 10 to the minus 8. And that's a number that you can remember, although you get sick of looking it up, but 15.69 times 10 to the negative 8. That's the sea level correction, and it's always negative. So it's just the mean height here, HA plus HB, which is the average height of A and B, times D, the horizontal distance in meters, times 15.69 times 10 to the minus 8. It's always negative. The correction will exceed 1 millimeter if the product, product is when you multiply things together, sum is when you add them together. Product of the distance and the mean elevation exceeds 6,000. So a distance of 60 meters, at 100 meters elevation, so 60 times 100, 6,000, or a distance of 300 meters times 20 meters elevation. If it exceeds that in those circumstances, then the correction will exceed 1 millimeter. If you, in each of those, it would just exceed 1 millimeter if you're going out beyond those. So there's sort of some rule of thumb. An accuracy of 10 millimeters per kilometer, or 10 parts per million, is achievable with an uncertainty of 60 meters in elevation. Okay, so that means if your elevations, you can be 60 meters out with your elevations, and it'll still give you that sort of accuracy for your sea level correction. So that means that you can generally get a level within 60 metres, just off the topographical maps that are available, and even some of the Google Earth and that type of thing. So, and just explaining here, provided mean sea level and the geoid are within 6 metres of each other, then any error caused by the difference will be less than 1 part per million. So this enables you to use ellipsoidal heights, which are becoming increasingly more available due to GPS, because GPS tends to measure in ellipsoidal heights very easily and very quickly. So yeah, you can use ellipsoidal heights, but just be aware that if they're within 6 metres of sea level, and there are people generally know where some of these areas are if this is of concern. Right, and now let's have a look at some examples here. So here we are, we've got HA 152.63, HB 247.56, a distance of 1476.321 measured horizontal distance, HA plus HB over 2, which is our H is 200.095. So the sea level correction would be 8 times D times 15.69 times 10 to the negative 8. It's 200.095 times 1476.321 times 15.69 times 10 to the minus 8, which is 0.046. So the corrected distance is 1476.321, remembering that's always negative, and when you're working at sea level and above, not the case if you're working below sea level, which does not happen very often. And that is gives us 1476.275. So that would be the distance reduced to sea level. Let's have a look at another one. 172.543, 168.307, and a measured horizontal distance 876.403. So just going through the same process again. 170.425 is our mean height. We multiply that by 170.425 times 876.403, 15.69 times 10 to the negative 8 equals negative 0.023. Apply that to our measured horizontal distance. That's the one we measured at the height, and we get 876.38. So sea level correction, pretty easy to deal with. Just a small correction, and we apply it. We reduce the distance to the horizontal, and then apply sea level correction. So all very good there.